A quick video, no camera, just my screen to talk about the next program we're going to do because it requires a little explanation. Those of you who have taken calculus are going to understand what we're doing and why in this program, and those of you who haven't are maybe not. But this is actually a good way to get a glimpse of kind of what calculus is before you take calculus, and I assume most people who are taking a class like this are probably going to take calc at some point. So we're going to look at a graph of a function. And we're going to look at a graph of the function y equals x squared, just a parabola, just in the first quadrant. In particular, we're going to focus on the interval from 0 to 1. And I'm going to ask this question. What is the area underneath that parabola on the interval from x equals 0 to x equals 1 on the x-axis? And that's actually y equals 0 to y equals 1, right? Because 1 squared is 1. So this point here is 1, 1. And I'm choosing a parabola just because it's a simple function, just because it's a straightforward function that I think we are all familiar with. The invention of calculus was in a large part inspired by problems like this, figuring out what the area is under a curve. At least the invention of calculus by mathematicians, the invention of calculus by Newton was inspired by some different concerns. But knowing the area underneath the curve, if you haven't taken calculus, just know that it is something that we sometimes want to do in mathematics. If you have taken calculus, you know this as an integral. The way we're going to approach this, and you may, if you've taken Calc 2, remember a derivation very similar to this, is breaking up that interval from 0 to 1 into segments. I'm going to break it up just into 3 segments and measure the areas of these 3 rectangles. We'll call them rectangle 1, rectangle 2, and rectangle 3. The sum of those rectangles' areas is close to, maybe a little bit more than, the area under the curve. If we divide our interval here into 3 pieces, each one has, so this is x equals 1/3, x equals 2/3, and x equals 3/3 from 0 to 1. These points are just the x values, x equals 1/3, x equals 2/3, x equals 3/3, or 1. The y values of these points are just the function y equals x squared. So this point is 1/3, 1/3 squared. 1/3 squared is 1/9. This point is 2/3 x. So the y value is 2/3 squared. 2/3 squared is 4/9. This is x equals 3. The y value is 3/3, 1. The y value is 1 squared, which is 1. So we can divide our interval into chunks and then find the x and y coordinates of those chunks. And those x and y coordinates are just the corner of a rectangle. So now we have 3 rectangles and we know their width. The width is all 1/3, right? They're all 1/3 wide. And the height is that the y coordinate, 1/3 squared, 2/3 squared, 3/3 squared. So the areas are 1/3 times 1/3 squared. That's the x times the y. The area of the green rectangle is 1/3 times 2/3 squared, the function of 2/3. That's the area 2. The area of the third rectangle is 1/3 times 3/3 squared. And that is, if we add those up, that's an approximation of the area under the curve. Now notice that there's a lot of overshoot here, right? There's a big chunk of this triangle that's above the curve. So this isn't going to be a very good approximation if we cut up our interval into 3 pieces. But if we cut up our interval into 10 pieces, it's going to be a better approximation, right? Because the amount of overshoot is even less. And if we cut it up into 100 pieces or 1,000 pieces or 1,000,000 pieces, the area of the rectangles when we add them up is going to get closer and closer and closer to the area underneath that curve. We could do this without the overshoot if we, instead of approximating these as rectangles, we approximated them as little trapezoids. So there are more accurate ways to do this, but we're just going to use this rectangle method for now because the coding is actually quite a bit easier. How will we know if the answer we get is right? What is the area under a curve? Well, the area under the curve is just something we call in calculus the integral, and the integral of this function, y equals x squared, from 0 to 1, is a known value. It's 1/3. So when we write this program to calculate this area, we should get as we make the number of slices bigger and bigger and bigger and bigger, we should get something that gets closer and closer and closer to 1/3. So in the next video, we'll code this. We will take that interval, we'll divide it up into chunks. We'll ask the user how many chunks to divide up the interval into, and we will compute the sum of the area of those rectangles, and we will see how close we get to 1/3.